Hi, I'm Janaky Murthy, and I work with Professor Rajesh Subramanian. My research topic is mean field gains on sparse network of interacting processes. We are interested in understanding systems that have a large number of interacting agents. These systems occur in various practical scenarios such as communication systems, queuing systems, neural networks, biological systems, and so on. And the interaction among the agents is modeled by a graph G with vertex set V and the edge set E. The vertex corresponds to the particle and the edges corresponds to the interaction. On the left is a complete graph where each particle interacts with every other particle, hence there is some sort of symmetry. Whereas on the right is a sparse graph where there are some missing edges. In my work, I'll be looking at this Erdos-Renyi graph where between any two vertices, there is an edge with probability P independent of the edges between any other pair of vertices. The dynamics of each agent depends on its own state, the state of its neighbors, and the action it takes. And we consider a game where each agent is intelligent and rational and chooses an action that minimizes some self-interest given by a cost function J. Uh, I'm going to set up this game in a very general sense. Sorry, I'm not going to set up this game in a very general sense. Instead, look for at a specific cost function, and let's try to understand this specific case. So this is an n-player discrete time game where the players can be in two states, 0 or 1, and the cost function is of a flocking type, which I'll describe later. The interaction is given by a graph G. In our case, it's the Erdos-Renyi graph. And the state of player V at time k is denoted by xv of k. We also look at the local empirical neighborhood, which is a probability measure on the state space. So it consists of the fraction of players in state 0 and state 1, a fraction of neighbors in state 0 and state 1 at time k. At each time step, the player V also chooses an action AV of k. It depends on two things, its current state xv and its local neighborhood mu v. This AV of k belongs to this set A, which is the closed interval 0 and 1. Observe that the action chosen is Markovian, and every agent only knows about its immediate local neighborhood and not the full state of the graph. Now fix a time horizon t, and the strategy of agent V is denoted as AV, which is nothing but the sequence of action taken by the agent V from time 0 to t. The collection of the strategy of the rest of the player will be denoted as A subscript minus V. Now, let me describe the dynamics. At time 0, the state distribution of the agent V is given by mu 0, and this is IID among all agents. From time 1 onwards, the state distribution of agent V evolves according to a controlled Markov chain. The Markov chain is controlled via the actions taken by the agent V at time k as follows. The transition matrix at time k is given by P of AV of k. So the action taken at time step k determines the transition matrix. Here we have defined the transition matrix as follows. So for example, the action taken is 0, then P of A is an identity matrix, which means the agent will stay at the same state. On the other hand, if the action taken is 1, then P of A is the transpose of the identity matrix, which means the agent will definitely flip to the opposite state. Whereas if action is 1 by 2 half, in that case, with probability half, the agent will stay in the same state, and with probability half, the agent will flip to the opposite state. Basically, A just says the bias the agent has towards flipping or staying at the same state. Now let's look at the cost function. Let AV be the strategy of agent V and A minus V be the strategy of the rest of the agents. Then the cost incurred by agent V has two components. One is the running cost. This running cost penalizes the agent for being biased towards switching or staying in the same states. If the agent is indecisive, then the running cost term vanishes. And there is a terminal cost. hence which contributes to the name flocking. So every agent V looks at its neighborhood. So xv of t minus mu v of t captures how the distance between the terminal state of agent V versus the terminal empirical neighborhood. So if majority of the neighbors are in state 1, then the agent V would also like to be in state 1. So that's what everyone is trying to flock towards the same state. So hence the name flocking cost function. And this is a mean field type game because the cost function depends on the mean field term mu v, and the action chosen, if you remember, also depends on the mean field term mu v. And it's given by the tuple, which I have written here. I'll not read it out. Now let's look at two definitions, which will be needed for the problem statement. First is the best response strategy. So let's look at the same game, and for any player V, fix the strategies of the rest of the players A minus V. Now look at all the consider the set of all actions and evaluate the cost J of. So if the action chosen by agent V is A, what will be the cost incurred if the others choose A minus V? That is J of A, V, A minus V. Now look at the argmin. This will be the best response. So first of all, observe that this need not be a single sense set. So there can be more than one best response to a given strategies of the rest of the players. So this Nash equilibrium is a standard equilibrium notion in game theory. So a strategy vector is called a Nash equilibrium if for each player V, the strategy of agent V is the best response to the strategy of the remaining players. So here the important thing to know is that this condition should be simultaneously true for all players. And so the natural question now is to ask about what is the Nash equilibrium of this game, right? So this answer to this question is known for a special case which are called mean field games, where as I explained in the first slide, the complete graph case where there is a lot of symmetry. Here they take the number of players to infinity, and due to symmetry, it suffices to analyze the behavior of a representative particle against a state distribution of the remaining particle. And this is called the mean field approximation. So let's pose the key questions informally now. Given a sequence of games, describe a simple tractable limiting game whose Nash equilibrium approximates the Nash equilibrium of the finite game for large enough n. In the last slide, we saw that mean field approximation is one such limiting model. So natural question to ask is, for what sequences is mean field approximation a good approximation? And even a slightly harder question we could ask is, what are the necessary and sufficient conditions on the sequence of games for the mean field approximation to work? Okay, so the mean field approximation is one limiting model. So there could be cases where the mean field approximation is not a good limiting model. So we want to consider cases where we have to find an alternative limiting model. And once we find the limiting model, the next question we can ask is, what is the limiting dynamics of a typical particle when all particle uses the Nash equilibrium strategies? So these questions are, although answered in the case of complete and dense graphs, these are open in case of sparse sequences. So sparse sequences means the average degree is uniformly bounded as n goes to infinity. For example, sequence of sparse ER graph. So right now my work focuses on this, and I just started literature survey and trying to set up the problem and find trying to mimic solutions from related areas to this problem. Thank you.